Hi everyone, we are Group 2 and we built a digital encryption accelerator. How does it work, you may ask? Well, I'm Lesego and I am the key.
Hi, I'm Matthew and I'm the input data.
And if we are XOR'd
on a Mukundi positive clock,
Session, I will be the output.
We engineered a lean, mean encryption machine that resets on command, wiping buffers cleaner than a blackboard.
Our system loads keys with surgical precision, 1 byte per clock edge.
we put it through the fire with C implementations, Python prototypes, and Verilog powerhouses.
Our system encrypts data in real time, taking data in and outputting data before the next clock tick.
The golden measure serial implementation uses an algorithm that processes data bytes sequentially using an XOR encryption with a rotating set of 4 keys. As you can see while running the program highlights performance characteristics based on the execution speed and number of clock cycles. For parallelization, we selected C with MPI due to familiarity of use and its scalability. The MPI version splits the input into chunks, distributes them across processes, and encrypts each independently, managing key offsets to ensure correctness. The master process reassembles the encrypted output. Similar to the serial analysis, the program highlights performance characteristics based on the execution speed and the number of clock cycles. MPI performance was tested from 2 processes to 32 processes for analysis.
Now that we have looked at the software implementation, let's see how the hardware performs. So, for our FPGA implementation, we defined 2 top-level modules, with the first one being a key register and the second one being the XOR encryption module. The key register module makes use of 4 input lines, with the first one being an 8-bit input wire DN. This is where our keys are set. For our implementation, we have restricted the maximum number of keys to 4, allowing us to iteratively encrypt the data using the same number of keys. Firstly, all internal buffers and registers are reset through our reset line. And then, while keeping K-set and D-clock lines low, our keys are fed through the DN line. The number of keys stored and the keys themselves are then fed as input to the XOR encryption module. This is where all the fun happens. The module itself can be reset through the reset line, and then, while keeping the K-set and D-clock lines high, our input data is fed through the DN line. This is then iteratively encrypted using the keys through the XOR algorithm and is made immediately available through our output data line.
So now we're going to look at the hardware description of our key register module. So the key register module makes use of a 32-bit register split up into 4 8-bit chunks. It then also uses a 2-bit counter to keep track of how many keys the system has. So when data comes into the system, we use the counter to split this data, well, not split, to direct this data into one of the 4 registers. When this is done, the system then increments its counter, therefore moving on to the next key. So when the next batch of data comes in, it's stored within the 2nd register. So this is done until all registers are full, at which point K-set can be set to 0 in order for the encryption to start. So this is our encryption module. This is responsible for performing the XOR encryption between the incoming data and one of our 4 keys. So we're using a counter to select one of our 4 keys. It iterates through each of our keys sequentially. this counter is fed into demux to actually select one of the physical registers. Once a register is selected, we can perform the actual XOR encryption. This produces an output which is then ANDed with our kset signal, which acts as an enable signal, with kset is equal to 0, allowing this operation to take place. So if kset is 1, then our output will always be 0, and if kset is 0, then our output will be the action of the actual encryption. So then on top of that, we've got reset coming in to reset our counter. Yeah.
Here we see the output of our Verilog test bench. This Verilog test bench is created in such a way that we see all the important data that we are looking for outside of our DEA. First thing to note is we have a reset button, and whenever that reset button is set to high, all the values are going to be set to 0. So if you look at time 11, you'll notice that key set, keys, D in and D out, and the current key are set back to 0. However, the first thing that we want to do is set the keys that we will use to encrypt the data. And at time 12, we see that K set is set to 1. And whenever we have a positive D clock and an input data, that data is then set to the keys. The keys are set to a 32-bit array that will be updated every time kset is 1 and we have a positive D clock. And at time 19, we have the full set of keys that are DDCC BBAA in hexadecimal, and these keys will be used to encrypt the data. When kset is set to 0, our system is ready for data encryption. We will loop through the keys array, collecting an 8-bit key that will be used to encrypt D in. On every positive edge clock, our encryption will happen. And as you can see, we loop through the current keys so that every encryption is done by a different key in the keys array. You may be confused by the repetition in D out. However, remember that our system only encrypts on a positive edge clock. As you can see, in time number 21, when D clock is 1, D out is EB. And when D clock goes back to 0, it is still EB. And this is because we do not do anything at a negative edge clock. So D out does not change. However, at time 23, when D clock goes back high, our D out changes. This means that we have the proper implementation and we have the proper execution on a positive edge clock. This is how our encryption implementation is happening. Also take note of how our current key changes. This is due to the looping through of the keys that are in the keys array.
Our analysis used a sequential C implementation as the golden reference for performance comparison. We analyzed the performance across data sizes ranging from 10 bytes to 10 megabytes. The shown speedup graph shows that while raw execution times show MPI outperforming the FPGA on large datasets, this doesn't account for clock speed differences, which is 3 GHz on the CPU versus 500 MHz on the FPGA. When normalized by clock cycles per byte, the FPGA shows superior efficiency, especially for small datasets. This makes it ideal in scenarios like network packet encryption, where small consistent-sized data packets require low latency processing to meet throughput and quality of service demands in secure communication systems.
This demo shows how our Python interface interacts with the Verilog-based data encryption accelerator. The user enters a short key and the message to encrypt. Python then writes this input to a file and compiles it and runs the Verilog simulation using Icarus Verilog. The Verilog module will then encrypt the message 1 byte at a time, taking into consideration that each letter in the sentence is a byte. It will then output each encrypted byte as a hexadecimal, and then Python captures this output and converts it to a readable character. Finally, we'll display the fully encrypted message, demonstrating that DA hardware logic is working as intended.
So this is our proposed system design. This would use the FPGA to encrypt a communications link between two PCs. So as you can see, the host computer would be connected to the FPGA via a physical cable or communications link. In this case, it could be an Ethernet connection. The output of the FPGA would then be fed directly to another host computer or through a decrypting system like another FPGA. So this would take advantage of the FPGA's real-time nature in order to encrypt a physical communication link between two computers. So the two computers could be communicating in real time with messages being passed back and forth. And these messages would be fully encrypted, protecting this communications link from data sniffers and other forms of attack.